Today let's go over everything we discussed in our electrostatics lecture. This includes electric charge, electric field, and electric interactions. First, let's talk about electric charges. There are two types of charge, positive and negative. Within an atom, the subatomic particle bearing positive charge is called the proton, and the subatomic particle that is negatively charged is called the electron. In a circuit, we talk about conventional current, which is the flow of positive charge. This is the current I. But really we know that flowing through a circuit are electrons. This is just sort of a silly matter of convention that you have to remember. The electric force is the means by which these charges interact. By Coulomb's law, the electric force, which is a vector, is equal to the constant k times the charge on the first particle times the charge on the second particle divided by the shortest distance between them, r squared. This is multiplied by the r hat vector, which is in the direction of r, the shortest distance between the two particles. We know that for any charges, opposites attract and like particles repel each other. So if you have a positive charge and a negative charge, the force will act along the line between the two, and it will force them towards each other because opposites attract. The electric field is a concept scientists use to understand how forces can act at a distance without any contact between particles. The electric field is equal to k times the charge generating the field divided by r squared. This is the distance that an imaginary test charge would be away from the original particle with charge q. We also know that the force on a test charge by an electric field is equal to the electric field strength E times Q. This is the charge on the test charge. Let's draw an electric field diagram for a positive charge. For a positive charge, the electric field lines point outward because this is the direction a positive charge would travel. It's also important to note that the distance between the electric field lines is proportional to the electric field strength. You can see that as you move farther away from this positive charge, the electric field lines are getting farther apart than they are closer to the charge. This means that the electric field strength is weaker here, which makes sense because electric force is proportional to 1 over r squared. So you expect that the electric field decreases as you move away from the charge. Electric field looks very similar for a negative charge, except that the electric field lines point toward the negative charge. This is because a positive test charge would travel toward a negative charge in an electric field. This is because opposite charges are attracted. It is also important to note that charge distribution differs in conductors and insulators. A conductor is an object in which charges can move freely, usually because the object is metallic and has many free electrons. In a conductor, because the charges can move freely, they distribute themselves on the surface of the object to get as far away as possible from one another. This makes sense because like charges repel each other. As all the charges will be concentrated on the surface, the electric field within the conductor will be zero. If the electric field were not zero within the conductor, the charges would still be moving. In an insulator, on the other hand, the charges are fixed and not free to move, so you can have an even charge distribution such as this. This means that the electric field inside an insulator does not necessarily have to be zero. Now let's talk about electric potential and electric potential energy. I like to think about these two quantities in terms of an analogy between electric field and electric force. This is Coulomb's law, the equation for electric force. And over here we have the equation for electric field strength. You might notice that these are very similar. They're both vectors pointing in the r hat direction. They're also both proportional to 1 over r squared. The only difference is the force is dependent on two charges because it's an attraction between two charges, whereas the electric field is independent of the second charge because we're talking about an imaginary test charge instead of an actual charge. This is very similar for electric potential energy, U here, and electric potential, V, which can also be called voltage. Electric potential energy is proportional to this second charge, whereas electric potential is not. It's important to note that both of these quantities are scalars, so not proportional to r squared. They're not in the r hat direction, which makes them different from the force and the electric field. That's all for now. Next we'll review some math dealing with electric interactions and electric fields.